very much, Karen, and thank you to the organizers for inviting me. I'm very honored to be here and get to speak to you. I'm also somewhat daunted because I feel like I sort of have to represent all of those computer architects, since I am talking about computing performance and what it has taken to stay on Moore's Law and to actually get performance benefits out of Moore's Law. I've decided to just, before I talk about science, which is really where I'm going to mainly talk about the impacts of that performance growth, I want to talk about some of the other applications we heard about this morning. So going back to Jeanette's story from this morning, if we roll back in time 20 years, or pre-1990 even, to a point where computers had the performance they did, but we had all of the innovations in algorithms, in software, in creative ideas for how to use computer that we've heard about throughout the day, I woke up this morning and I decided I wanted to access my gigahertz processor, and it was a Cray YMP sitting in bed with me, which is, fortunately, it was designed to be a little bit smaller than the previous generations of Crays. It weighs under a ton, but it's still a fairly dominant force there in the bed. And then I decided I wanted to do a Google search, but the networks are really not up to the kind of bandwidth that I wanted to get because I wanted to search for images. So I'm going to drive to my local Google Center. Of course, that Google Center is requiring tens of gigawatts of power to get the kind of computing performance. And because Google is a very green company, they put this by a hydro dam. The one that I think might possibly have provided enough performance is in China at Three Gorges Dam. So this is, it is about computing performance, hardware, the energy efficiency of hardware, in addition to all the innovations that, of course, have been absolutely critical in getting the kind of applications that we've heard about today. So I'm going to talk here. Let me just get my clicker. Though a little bit about high performance in science, what it has done for science, and also what some of the challenges are in continuing to increase computing performance that we need for the future innovations in science. I'm going to really talk about three different classes of problems and just give you an example. These are taken from the DOE space, Department of Energy space, and they're taken specifically from things that were done on the computers that are used at the NERSC Center. But I'm going to talk about science at the largest scale, so enormous problems that use some of the largest petascale systems that we have today. Then I'm going to talk about more of the volume problem of computing. That is, where you want to run massive amounts of massive numbers of simulations in order to make a scientific discovery, and then finally say something about data. So this first example is taken from Combustion Simulation. It is maybe something a little harder for most of us to get our hands around than something like a Google search or reading your email, but it's really about designing very energy-efficient devices in order to generate power. And what you see there is, I think I picked this example in part because I think it's a great example of the three pillars of science working together. The picture of the scientist there is an experimentalist, Robert Chang, at Lawrence Berkeley Lab, who's designed something called low-swirl burners. These are very energy-efficient, low-emissions burners that he designed, partly inspired, by the way, by his dryer. So it was about how you make enough heat in order to dry your clothes. And you can see from the right-hand pictures that they come in all different scales. So he's actually licensed some of this technology to industry, and they are they're small enough to hold in your hand, or industrial-scale burners to create large amounts of heat. And so but they're trying to understand how to move these kinds of burners into alternative fuels and really understand the process of combustion and exactly how to design the burner for the fuel injectors and things to maximize their energy efficiency. And the simulation there that you see on the left is one of these low-swirl burners. This was done by John Bell, who's an applied mathematician. That simulation requires advanced math and advanced algorithms. In fact, it was one of the examples that David gave in his slide. But what this really allows them to do is slow down the burning process so you can see exactly what's happening. And there are features in this that you can't see actually in the lab. They run these simulations today on some of the largest petascale systems, such as the Jaguar system at Oak Ridge National Labs, as well as the NERSC systems. But they need exascale computing to put all of the chemistry in to understand the alternative fuels that we want to develop. The second example is computing in volume. And this is used for everything from screening from diseases to batteries. An example from the University of Washington, Valerie Daggett's group has a project, the Dynamiomics database, which is to improve the understanding of basic structures like proteins. And she ran 10,000 simulations of the NERSC systems and has used these to understand some of the basics of drug design. That is, what they actually stored now in this database is all of those 10,000, 11,000 simulations, but it's not just the result of how the proteins fold, it's the actual dynamics. So think about storing, it's basically a Netflix database of protein unfoldings, which is what the simulations are. And they've been able to understand something about the common patterns and how these fold that are behind things like Alzheimer's disease. The example on the right is a project that has been done by Gert Cedar at MIT and Kristen Pearson at Berkeley Lab. It's the Materials Genome Project. It's the idea of simulating massive numbers of things, in this case applied to the problem of designing more energy efficient and useful and with long life batteries. The goal here is actually to improve the productivity of companies that are making these batteries by cutting in half the about 18 years that it takes from the design of a new material that could be used in a battery to its use in manufacturing. So it's trying to shrink that by about 50%. They simulated, in this particular case, 20,000 batteries. I won't go into the details of what's in the graph, but it shows you kind of where current batteries are at. And what this does is that lower right quadrant is the place where there's interesting materials. So you can narrow down your space of interesting problems by doing massive numbers of simulations. They asked for a startup account at NERSC, and they put in their request for next year. It was a fifth of all of the computing that we have at NERSC. I said, I'm sorry, I can't quite give you that much computing time, but it gives you an indication. And by the way, they would like about 10,000 times more computing to solve, to put all of these materials into realistic situations. So once again, an exascale volume problem. The last example starts with the Nobel Prize story from 2011. There's a picture of Saul Perlmutter, who won the Nobel Prize in physics, so was one of the winners. And this was using type 1a supernova to use as standard candles, so measurement devices, to understand the expansion of the universe and the acceleration of the expansion of the universe. This was based on simulation. So how do we know what supernovas are supposed to look like from the Earth? Well, in the late 90s, they did simulations of what they were supposed to look like, and that allowed them to use those as these standard candles or measurement devices. More recently, a problem that's even more data intensive is looking at, it was a discovery of a nearby supernova. Peter Nugent, who also works at the lab, had made this discovery when we had, I think not coincidentally, made an upgrade to the global file system at the center that allowed them to sift through the data much more efficiently than they had, and they produce about 300 gigabytes per night of data sent through the ESNet network to the NERSC Center. There are machine learning algorithms that sift through that data and look for things that look like interesting features that might or might not be supernova. Peter then was looking at these one night on this optimized file system and realized that it was something that looked like a supernova. He happened to see that within hours of its initial explosion, which is the earliest. So even though it's 10 million light years away, and of course happened a long time ago, it allows him to capture what's a very short window of a couple of weeks. And they redirected telescopes in order to get a never-seen-before pictures of what that supernova looks like early in its explosion. I think NITRD has really moved scientists through some difficult technology transitions and have more of that to do as we look forward. This is also looking at some of those numbers from the Gordon Bell Prizes. These are scientific applications running at very large scale on some of the largest systems in the world, and just kind of showing you what happened. Well, what did things look like in the early 90s? Well, something really dramatic happened, which was what we sometimes refer to as attack of the killer micros. So those pictures on the bottom left, some of those are Cray systems, like the large supercomputers, vector supercomputers, which were designed specifically to do large-scale scientific simulation problems. And these killer micros, of course, came in, which was both an opportunity to have more cost-effective way of building these systems, but also really a crisis for the scientific computing people who were trying to write the software, because it completely changed the way you write the software. So let's look a little bit. This is data now from the top 500 list, looking at, it's a great historical reference for what some of these fast machines in the world look like. So the fastest 500 machines that are reported, at least in the top 500 list. And what I'm looking at here is, what is the processor technology that is used within these high-performance computing systems? And over this roughly 20-year, 18-year time span in which NITRD has been doing a lot of this research. So on the left-hand side, you see that the chart is dominated by these red-colored, which are vector processors, shared memory multiprocessors, so single processor systems, and small shared memory SMP systems made out of vector processors. Those dominated the fastest machines in the world at that time. On the right-hand side, they're completely gone, and everything is either a cluster or a massively parallel system, which is basically a cluster with a more highly optimized network designed specifically for massive parallelism. So in that same period of time, the number of industrial machines on that list went from 25% of the list to 50% of the list. So we can see that this has had a real impact on the use of large-scale computing in industry, because these machines were now much more accessible from a hardware standpoint. It's much easier to go out and buy a cluster. However, there was still there was a big problem, which is how to program them. So the other way to look at this is that, very roughly speaking, those early systems were programmed by annotating serial programs, and whereas the new systems had to be programmed by completely rethinking the algorithms and the software for parallelism and message passing. So David mentioned the MPI library, the interface, which is one of the things that NITRD has made a number of investments in. This effort and the standardization effort was first started in 1992. They did the first release of an MPI implementation in 1994. It involved 80 people from 40 organizations spread throughout the government and throughout the world. It scales to millions of processors today with separate memory spaces, so it's very scalable, and it's very portable. It's allowed, you can use multiple programming languages. In fact, when we look at NERSC, many people are using multiple languages in their large-scale scientific applications. Very complex applications that often tie together these libraries as well as simulations that came from different communities into a multi-physics simulation. And billions of dollars of applications have been developed. And of course, it's not over. As the systems continue to evolve, the MPI implementation standardization effort has to evolve as well. Now, the programming challenges here, and this is just kind of giving you a summary of a number of different scientific libraries that were built by NITRD-funded projects from the agencies, and it includes, I looked at how many of these applications are used in some of the NERSC workloads. We have 4,000 users at NERSC, about 500 different projects, and those projects, about 35% of them, for example, use the LAPACK linear algebra library funded by NSF, later funded by DOE. The PET-C library that David already mentioned, FFTW, which came from MIT, also had funding from those agencies. In a number of these different libraries, I won't go into details, but this really allowed people, the MPI basis and then the libraries that were built onto it that have some of the state-of-the-art algorithms encoded into those libraries have really fueled a lot of these applications that you saw earlier. I will just say that MPI is not the only kind of innovation that came up in basic programming. MPI is mostly used for these problems that you can decompose, a physical simulation problem that you can decompose into these different parts, which you see in the images on the left, for some of the problems that come up in security applications and come up in some of the kinds of social graph analytics problems that we're trying to solve today, and have actually been trying to solve for a number of years. There's a very high random access problem that comes up. That is, you want to just sort of grab any data anywhere across the machine. Bill Carlson calls this the just do it sort of phenomena of programming. Sometimes, even though it's very expensive to grab 8 bytes of data across the network that's all the way across the machine, you just need to do it. And so a number of languages, including languages I've worked on, but also things that were funded by DARPA and the HPCS program, X10, Chapel, and Fortress, have all been based on this kind of model to make it easier for people to write these kinds of programs that don't easily decompose. In some sense, what you're trying to do there is find the structure that doesn't already exist a priori. So going back to looking at this graph of performance growth, of course, the other major thing that happened was in 2004, the rest of the world got parallelism. And people looked to the expertise and the people that suddenly it became very hard to hang on to your experts in parallel programming because everybody wanted to hire them. It was no longer just something for scientific and engineering disciplines. And now, as we look forward, there's a question about how are we going to get to an exascale, and the question I have here is are we going to see something like the attack of the killer cell phones between now and then? We really need to make these systems more energy efficient and therefore maybe looking at these kinds of cell phone devices. So many of you people in this room, of course, are very familiar with what Moore's law really is, which is about transistor density. It is not about performance. And of course, and Moore's law is alive and well today, and it looks like it'll go forward for at least close to another decade. But the clock speed frequencies have not continued with Moore's law. And in 2004, something very dramatic happened where basically the clock speeds leveled off. And the reason they did that was because of power density. Your laptop is now too hot to hold on your lap for long periods of time. And that is the same problem that we see when we build large-scale systems. Instead, what we're seeing is a growth in the number of cores per processor. And so the scientific community, along with everybody else, have had to deal with this particular problem. So at the very large scale, what does this power density problem translate into? Well, it also translates into a problem for those of us who are facilities directors. These are megawatts of computing facilities, whether you're talking about a cloud facility used for a wide variety of applications, or you're talking about a high-performance scientific computing with systems and networks optimized for science and tightly coupled problems. The problem is really how do you build more computing performance for for the entire computing community? And it's, we've got a petaflop machine. It's about 3 megawatts at NERSC. If we were to try to build an exaflop with that technology today, it would require about 3 gigawatts, of course, of power. But if we speculate out to what Moore's law will give us in terms of energy efficiency improvements, it's still about 130 to 200 megawatts. And so this is really the problem we have going forward. And it's not just about how to build the largest system, but about how to build all the systems. The inspiration, then, of cell phone processors as very energy-efficient devices, graphics processors, also very energy-efficient, are really going to change the nature of computer architecture. And there's a lot of research that has to be done to figure out how can we leverage these kinds of devices. Anybody who thinks that this problem is solved or is kind of on an obvious path just needs to look at what I think of as the chaos right now in the computer architecture industry in terms of what is going to be the way of getting more performance going forward with graphics processors and others. The real problem is also then, besides redesigning the hardware, we need to redo the software and algorithms. This graph looks at the amount of energy used to do various operations. Communication is the thing that's important. Computation from both a time and a energy perspective is relatively free. And so the conclusion from that is, contrary to what your spouse tells you, stop communicating. And I will end with just a cover of a National Academy's report, NRC report that I was involved with. I think Bob Cole and others were involved with this. It was computing performance game over or next level. Sam Fuller, who led that study, calls this graph the expectation gap graph. It says that as things turned over, I think everybody in this room implicitly assumes that computing performance will continue to go up with Moore's law. But there is going to be a lot of work, even more than there was in the last 20 years, to make that happen in the next 20 years. Thank you.
Time for a quick question for Kathy.
Here? Yes.
You got a spot mic?
So I understand completely the kind of problem that you're dealing with when you're trying to scale to more machines and volume and the like. But I'm wondering if you've had any examples that you could cite where the solution to progress was more in the line of doing not so much even special purpose application-specific chips or things like that, but literally machines that might do the computation. We've had several examples where we've dealt with physical things that involve thousands or millions of independent things that had to be controlled, and where a device was a better solution to it than a computational approach in the normal sense of that term. Have you had any of those examples, and if so, could you share some with us?
Well, I'm not sure if it's exactly what you're referring to, but we have looked at the problem of how would we design a computer system specifically for science. And not so much because we think we're going to go and build that thing, but because it tells us a lot about what we can and can't use. We had a project called Green Flash, which looks at using these kind of cell phone processors and tailoring them to scientific simulations. And you can get much more energy efficient and powerful systems by doing that than you can by using kind of commodity x86 sort of processors, even if you scale those forward in time. I think that we are going to also see, I think, more specialization on the chip for different kinds of application domains, and trying to figure out how to take advantage of that and how the scientific community takes advantage of what the rest of the world is going to do, I think is one of our big challenges as well.